The last few classes we were looking at what is known as the integration of functions with respect to a measure. Right. So in the last class we looked at what is known as the so-called monotone convergence theorem. One of the important aspects in the context of integration theory. Right, so this is one, and then we had several corollaries to this monotone convergence theorem. Right. So natural question is that, so if you look at the statement, well, let's state the statement. So let Fn be a sequence of sequence of, I'll simply say sequence of 0 to infinity valued Borel measurable functions defined on Meha A. Then, so if, well, I'll need one more, such that Fn is less than or equal to Fn plus 1 for all n in n. Then integral over omega limit of Fn d mu the same as limit over n integral over omega Fn d. That is the integral and the limit, they can be interchanged. Fine. This is one of the things that we had. Fine. So remark, maybe I'll put a remark here that in the above theorem, or well, I'll write it this way. The above theorem holds even if we assume Fn less than or equal to Fn plus 1 almost everywhere. So you don't need this to hold everywhere, but if you can assume that it holds only almost everywhere, then still it's, yeah, just give me a minute, huh? Yeah, I'm sorry. Yeah, so you don't need Fn less than or equal to Fn plus 1 everywhere. It's enough if you can have it only almost everywhere. The same proof works. Yeah. So maybe I'll add one more corollary, or maybe so maybe I could have added it as another remark, because well, let me put it this way. So here we did not say anything about this one limit. So we only it was written is that integral over omega limit of Fn is same as limit of the integral. Integral of the limit is same as the limit of the integral. So by which it is clearly understood that whatever we are taking as the limit, it's the pointwise limit. Fine. So what happens if we replace it by almost everywhere limit? Oh, sorry. If we replace it by almost everywhere limit. So if Fn is a sequence of zero to infinity valued Borel measurable functions, defined on omega a mu such that Fn increases to f. So they are increasing and they increase to f. So it's an increasing sequence and they increase to f, and this convergence is only almost everywhere. And we know that almost everywhere sequence of a measurable functions, so the limit need not be again measurable unless and until the space is complete. But something more is known to us. What is that is known? If Fn converges to f almost everywhere, f need not be measurable, but something more can be said.
And F is equal to G, where almost everywhere G
So
is
you
measurable.
can make it into measurable. The limit can be made into a measurable function. So without loss of generality, we are going to assume that where f is a measurable function, then so still the same conclusion holds. Integral over omega f d mu is equal to limit of integral over omega f and d mu. Yes. So even if the convergence is almost everywhere, the same conclusion holds. Proof. So since Fn increases to f almost everywhere, there exists E in A such that Fnx increases to Fx for all x in E, and the measure of E complement is 0. Yes. So now, what can you say about f minus f times chi E?
Zero almost everywhere.
This is going to be 0 almost everywhere. So which is very important. Yes, so others, why is it 0 almost everywhere? Yes, Ankit.
So it is 0 on E, and where it is non-zero
E complement where measure is 0.
Exactly. So on E, chi E is 1 and therefore so it's only fx equal to fx. On E complement, chi E is 0. And also not only that chi E is 0, measure of E complement is 0. Right? So this is 0 almost everywhere. Right. Therefore, integral over omega f the same as, so integral over omega f into chi E plus chi E complement. So which is same as integral over omega f chi E plus integral over omega f chi E complement, which is same as integral over E f plus integral over, well, what will happen to the other one? F chi E complement, the function is, this function is going to be 0 almost everywhere. So this is going to be 0. Now, on E, what is f? This is the pointwise limit of Fn. Now by monotone convergence theorem, this is integral over E Fn by monotone convergence theorem. Now again, we can repeat the same thing and then say that this is same as integral over omega Fn. That's it. Right. So we haven't lost anything. The same conclusion holds even if we replace pointwise convergence by almost everywhere convergence. Right. So natural question is that, can we replace? Do we actually need increasing sequence? Let's look at some simple examples. You look at R, Borel sigma algebra, and the Lebesgue measure. Choose Fn as the characteristic function of the interval n comma n plus 1. N in n. So where does it converge to?
0.
0. Why? Why does it converge to 0?
Because sir, after when n is greater than equal to, we have considered some n naught, and after n naught plus 1, all will be 0.
Right. So the function, so note that Fn converges to 0 pointwise. So these are not increasing function. First thing. Second thing, what is integral over R Fn?
One.
1. But which doesn't go to 0. Right? So which means that it doesn't hold for arbitrary sequences. Right? Let's look at one more. You look at 0, 1, and then again the Borel sigma algebra, the Lebesgue measure. Choose Fn as the characteristic function of 0, 1 by n. Right. So where does it converge to? Where does it converge to?
0.
0. Fn converges to 0 pointwise. Again, why?
Because for any x there exists an n such that n is 1 by n is less than that x, and hence at x.
Fine. Fine. Now, so this converges to 0 pointwise. And second thing is that you can notice that Fn is bigger than or equal to Fn plus 1. It's a decreasing sequence. Sorry, I need something more. Sorry. Yeah. I need this n. Sorry, it is not decreasing. So again, sorry. I need this n. Sorry, otherwise, yeah, first thing. Now, integral 0 to 1 Fn. What is integral 0 to 1 Fn?
One.
1. Again, which doesn't go to 0. Right. Fine. Right. So now, yeah. So the most important one here is, so next corollary. Well, there are a few more corollaries. Well, so let f from omega to 0 to infinity be a Borel measurable function for E in A. Define nu of E as integral over E f d nu. So the mapping E going to nu E defines a measure on omega comma E. So this more or less the same proof. We have almost done the proof with a small change. Otherwise you can do it. Fine. Fine. Next one. Next important one in this context is what is known as Fatu's lemma. If Fn is any sequence, so of 0 to infinity value, measurable functions, then see, we were only looking at increasing sequence. So now what happens in the case of an arbitrary sequence? So there we were only speaking about increasing sequence, therefore we can speak of the limit. We can speak about the limit, which is nothing but the supremum. Well, it can be unbounded. That's a different thing. Now, the natural question is that if you have something like an oscillating sequence, so in those cases, at most what you can speak is what is known as the lim sup and lim inf. So the maximum that you can expect is integral over omega lim inf fn d mu is less than or equal to lim inf integral over omega fn d mu. Right. So for each k greater than or equal to 1, what do we have? Infimum over n bigger than or equal to k fn. So notice that this is less than or equal to fj for all j bigger than or equal to n k. For all j bigger than or equal to k, fj is bigger than or equal to the infimum over all fn's with n bigger than or equal to k. Therefore, integral over omega infimum over n greater than or equal to k fn using the monotonicity of the integral. So this is less than or equal to integral over omega fj for all j bigger than or equal to. So now this is true for all j bigger than or equal to k, and therefore this should immediately tell us that integral over omega infimum over n greater than or equal to k fn is less than or equal to infimum over j bigger than or equal to k integral over omega fj. Right? Now, so now if you look at this one, so let me call gk as infimum over n bigger than or equal to k fn. Yes. Now, what can you say about gk?
It is an increasing sequence.
It's an
Increasing
sequence, right? And it increases to lim inf. So gk is an this is an increasing sequence, and increases to lim inf fn. Right. Therefore, integral over omega lim inf fn, this is nothing but integral over omega limit of gn, which is same as, now gn's they are increasing sequence, therefore the limit and integration they can be interchanged. Right. Now what are these gn's? they are nothing but infimum over k greater than or equal to n fk. Right, so this is by monotone convergence theorem. That is very important. Yes. Right. So Gn is this one. Now we have something here. So we are going to use this. Maybe I'll call this as 1. So I'll have a less than or equal to limit n tending to infinity infimum over j bigger than or equal to n integral over omega fj. This is by 1. Right? And this is exactly the limits of this sequence. That's it. Right? Fine. So now there is a small example in this context showing that there is a strict inequality. Look at the example. So you consider the measure space 0, 1, Borel sigma algebra, the Lebesgue measure. The same function fn is n times chi 0, 1 by n. Right. Yeah, this was the function and we observed. So this is what we observed. Fn converges to 0 pointwise. So integral over Fn doesn't converge to 0. That's what we observed. Right. Fn converges to 0 pointwise. Therefore, the lim inf is again 0. Right. So therefore, integral 0 to 1 lim inf Fn is, so here in this case it's exactly limit, because the limit actually exists, so which is 0. But limit of, well, what we wanted is the other way. Lim means Fn, so which is 1. So which means that integral 0 to 1 lim inf Fn is strictly less than integral 0 to 1, well, strictly less than lim inf of integral 0 to 1 Fn. Yeah, your left hand side is 0, right hand side is 1. So therefore, so that is strict inequality can hold in Fatos's lemma. Right. Fine. Now let's move further. Right. So let me before I proceed, let me give some exercise. These are easy exercises. If f from omega to 0 comma infinity is a Borel measurable function and if integral over omega f d mu is finite, then show that first one is that measure of all those x in omega such that fx is infinity. This set has got 0 measure, and second, all those x in omega such that fx is finite is a sigma finite set. Right. This is a sigma finite set. Right. So now the natural, so we have been doing integration only for positive functions, extended positive functions, Borel measurable, of course. So now the last stage, well, third stage, omega to r bar be any Borel measurable function. So how does one define the integration of this? So define two functions f plus and f minus, the positive part and negative part. So 0 comma infinity. How are they defined as? They are defined as f plus at x. I will define it as f plus of x is fx if fx is bigger than or equal to 0, 0 if fx is less than 0. Similarly, f minus of x, you define it as fx if fx is less than or equal to 0. Well, I need a minus 0 if fx is bigger than 0. Yeah, so a few things that you can observe is that since f is measurable, both f plus and f minus are measurable. Second thing is that you can write f as f plus minus f minus. It's a linear combination of two positive functions. Right. Now, how do you define the integral of f? How do you define? The integral of f.
As sum of these two integrals.
Sum of these two integrals.
I mean, integral f plus over omega minus integral f minus over omega.
So suppose that both are infinity. What is infinity minus infinity? We did not say that they are finite.
Yes, sir.
We did not say that they are finite. So well, so now define integral over omega f d mu as what Sneh said. It is integral over omega f plus d mu minus integral over omega f minus d mu, provided at least one of the integrals is finite. At least one of them should be finite. Only then you can define the notion of integration. Right? Otherwise, this is called as it is infinite. The value is just infinite. There is no question. Right. So a good exercise here is that, well, before I state the exercise, so here one more thing that you can, maybe I'll put it here. Yeah. So we start. So f we wrote it as f plus minus f minus. The third thing that you can notice is that mod f can be written as f plus plus f minus. Yeah. Right. So we say that f is integrable if integral over omega mod f d mu is finite. Right. So good exercise here is that show that f is integrable if and only if both f plus and f minus are integrable. That's it. Right. So lemma. The first lemma is that the space of all, well, I cannot call it a space as of now. I can only call it a set. The set of all integrable real valued functions defined on omega, well, omega a mu forms a real vector space or R vector space. So by the way, what is a vector space? What is a vector space?
A set with
Give chance for others. Let others also answer, please.
Group under abelian group under addition and abelian group under multiplication with distributive law of
Multiplication.
Yes, sir.
I don't know what kind of multiplication is here. Bishop Prakash. I don't know. Well, I understand that there is a It is with respect to addition. There is an operation called addition, with respect to which it becomes an abelian group. Very good. And then, what kind of multiplication do you have?
Scalar multiplication, sir.
Scalar multiplication. With respect to scalar multiplication, what is happening?
Closure axiom holds.
Fine.
And one identity also holds.
What are the identities? Distributive with respect to what?
Distributive, like sir, if A is scalar and U and B are vectors, then
there are two distributive. See, which one distributes which one? Scalar multiplication distributes over the addition in the vector space, the addition in the vector space, or addition in the scalars. There are two addition. There is addition on the field, there is addition on the space, that is V. In fact, it distributes over both. And then, next. What is that identity? You said some identity.
So like 1 is multiplied, then 1 dot U equal to U, sir, for all vectors.
1 dot V is V, which is very, very important. This is one of the important axioms. And why is it important? Why is it important? It tells you what the scalar multiplication is explicitly. That's the whole thing. Well, so let's not get into these things. Right. Yes, so now let's get into the proof, because I don't have time, but still. So it's a huge proof. Well, it's not that huge. Okay. Yeah, let me just take 2 more minutes, and then I think I should be able to write. Yeah. Right, so now let f and g be integrable functions, and let alpha comma beta belong to R. Then, so first thing is that mod alpha f plus beta g. This is less than or equal to mod alpha times mod f plus mod beta times mod g. Therefore, this will imply that integral over omega mod alpha f plus beta g. So if we can show that this is a finite quantity, then we are done. This is less than or equal to integral over omega mod alpha mod f plus mod beta mod g d nu, right? Again, use the fact that integral split distributes over addition. Again, so these are positive scalars, mod alpha and mod beta, therefore they can be brought out. Right, and each one of them, they are integrable, which means these are finite, and therefore, and mod alpha, mod beta, they are only scalars, finite real numbers, therefore they are finite, and hence this is finite. That's it. Right, and we are done. Fine. All right, so I'll stop here. Tomorrow we'll see, that is on Tuesday we'll see something more. That is the integral is actually a real linear functional on the space of integrable functions, which is one of the important things that we are going to see. And then how does one go about integrating complex valued functions? And then an important theorem in this context, what is known as the so-called dominated convergence theorem, which is again very, very important. Right, and I think with that, integration should get over and we should be able to start the inequalities that are needed to show the completeness of the LP spaces. Right. Okay, thank you all.